large-scale energy production. It's essentially limitless in terms of fuel supply. It doesn't produce greenhouse gases. I guess the only differentiating features with respect to fission is that it has lower long-lived radioactive waste and it is intrinsically safe. Although, as we've heard, there are also intrinsically safe next-generation fission power plant designs as well. So the idea of it is that you need to bring two positively charged atoms together close enough to allow the nuclear binding energy, the strong force, to take over. And for this to happen, the particles have to be extremely energetic. So if I look at the cross-section for reaction, this is the cross-section for the DT reaction. It peaks at around about 100 million degrees centigrade. So the constituent particles have to be extremely hot. The other properties that you need is that you need a large density, because this is proportional to the energy yield, and you need a large energy confinement time, which is like an insulation parameter. If I boil that jug of water, the time that it will take for that jug of water to cool down is a measure of its energy confinement time. And if I do a simple power balance analysis to work out the power loss to be greater than the heat loss, I end up with some confinement threshold which tells me that this triple product has to be bigger than a certain number in order to make power. At these very extreme conditions, matter exists in the plasma state. So what's the plasma state? If I look at the gas in this room, all the electrons are bound to the ions. So we have complete atoms which are neutral, and if I impose a strong magnetic field, nothing will happen unless you have a pacemaker. However, if I strip the electrons off the ions, I'll end up with the charged superparticles. And if I now apply a very strong guide field, or a magnetic field, the charged particles will start gyrating around the field lines. Nearly all of the visible universe is in this plasma state. So what the idea of toroidal magnetic confinement is that you want to use this very strong guide field to confine the charged particles, which are the alpha, the deuterium, the tritium, and the electrons, whereas the neutrons have no charge at all. They're not confined. They go straight through the vessel and impact the wall. Clearly, if I had this device linear, the plasma would just fall out the walls. So the simplest way of making this into a closed geometry is to bend it around into itself. And the most successful magnetic confinement device of this class is called the tokamak, which has a very strong guide field, and it's a Russian acronym for toroidal magnetic chamber. So what does a tokamak look like? It's got a vacuum vessel in which you put the gas, which you're going to ionize. You have some strong toroidal fields which produce this really strong magnetic field which is around the device. You then put a transformer limb around this, and you swing the transformer in one direction. And you might remember from second year electrodynamics that if you swing a field in one direction, at least if there's a current conducting surface nearby, you will induce a current in the opposite direction so as to oppose that magnetic field. That's what happens here. So you introduce a large toroidal current. That toroidal current produces poloidally confining magnetic field, and you have additional shaping coils. So what you produce from all of this is a big magnetic bottle. So the idea is that now the particles lie. If I look at the trajectory of the magnetic field lines, they circulate both the long way and the short way around the torus, and the particles are gyrating around these field lines. In an ideal tokamak, one which is completely symmetric, you have lots and lots of flux surfaces, and really the plasma physics challenge now becomes more of an insulation problem. What you want is you want the core of this to be 100 million degrees centigrade, and across each of these surfaces you can support a pressure jump or a pressure gradient. So you want as many of these surfaces as possible to maximize your core confinement. How do I heat it? I need to heat it to these ignition temperatures. Well, it's a combination of ohmic heating. Ohmic heating peters out around about 3 keV, which is about 30,000 Kelvin. 30 million Kelvin. In order to heat it to the 100 million Kelvin, I use a combination of electromagnetic heating, which is the same technology used in a microwave, and big neutral beam injectors, which are basically which is a bit like billiard ball physics. What you're doing is you're firing a neutral particle into the plasma, because it has to have no charge, otherwise it will be deflected by the magnetic field. It then undergoes some charge exchange reaction, and the highly energetic atom is captured inside the plasma, together with DT heating. So if I look at the progress of this as a function of time, I mentioned that the early phases of this started from the post-war period. The fusion triple product was down in the basement somewhere at that time. But really the fusion triple product has increased since the early 1960s up until around about the break-even now. And the break-even point is this joint European torus, which it didn't quite achieve it, but it got very close in 1997. That was some time ago. The reason why it hasn't gone into that phase is because it needs to operate in a DT cycle, and it hasn't operated in a DT cycle since that time. So it could go above this, and in fact there is a plan for it to go into a DT campaign later this year to exceed that Q of 1 value. But mostly the machine is limited to about Q of 1, so there's not really much physics that you can demonstrate. You might be able to demonstrate a political stunt, if you like, to show that you can generate positive power, but you can't actually do any useful confinement physics in a higher regime. What you want to do is you want to lift this power gain above. What you really want to do is turn the auxiliary heating off altogether, where Q approaches infinity. It becomes a power plant. So what you're doing is you're turning off all the heating altogether. The burning regime, which is the next step experiment, which is this fusion experiment, will explore this Q of 5 regime, and that's where the auxiliary heating is equal to the fusion power internal heating. This next step power plant experiment is ITER with a power gain of 5 to 10 in steady state. It's a 500 megawatt device. It doesn't produce electricity. It's a research experiment, but it's very big. There's a person for scale. There's lots of collaboration agreements with the IAEA, CERN, Principality of Monaco. Hopefully there will be one with Australia soon, which Anstove is now in discussion with ITER about. And curiously, earlier this week, Iran had a high-level delegation to ITER. One might also suspect that Iran has other interests, not weapon-related, but Iran is trying to make progress in terms of demonstrating to the community, international community, that it's interested in atomic power for peaceful purposes, and this is one way of doing it. Construction plus 10-year operation cost, well, it's a lot of money, and that estimate is very conservative. It's probably double that by now. But that's not uncommon for a big physics project. CERN ran out of money. In fact, CERN had to borrow money from the banks in Geneva in order to be able to complete its construction. What are the ITER objectives? Well, it's to demonstrate feasibility of fusion energy for peaceful purposes, explore a whole bunch of fascinating physics that interest me, particularly this burning plasma science where the plasma is self-organised. There's also a technology angle in the sense that one aspect of ITER is to demonstrate this integrated operation en route to a power plant, but there's also a crucial materials issue because these are generating 14 MeV neutrons. The neutrons can damage the surface or damage the structure itself. And the structure, not so much of ITER, but the structure of a power plant needs to be extremely resilient to this very high neutron flux. So that's a challenge that I guess fast neutron fission and also fusion have to a degree in common. Here's a detailed picture of it. So it has nearly 300 lightning bolts of current flowing around it. Its plasma volume is about a third of an Olympic swimming pool. It has 73 megawatts of auxiliary current drive. And this toroidal field is superconducting. It's about 5 Tesla in the core. So to make a superconducting field, you have to use superconducting magnets, which are niobium tin. They're cooled down to 3 Kelvin. So you're going down from 3 Kelvin to about 100 million Kelvin in about the space of about 2 meters. So it's a pretty extreme experiment. As I said, there's lots of plasma physics experiments, plasma physics challenges. There's new instabilities that occur in burning plasmas where you have these where you have the products of reaction driving various electromagnetic modes. This is fascinating physics. There's something called edge localized modes, which are a bit like filaments that erupt out of the sun. So if you look at solar flares, for example, this is a pretty reasonable analogy in the sense that you have these magnetic flux ropes that erupt from the edge of the plasma edge, and they can carry up to 10% of the stored energy of the device. And the consequence is that if that lands on one of your tile is very unhappy. Together with a combination of technology really for control and also modelling and integration. Here's some material choices for ITER. ITER will have a combination of this beryllium first wall, chosen because it has because there's relatively low heat flux, but it's also low Z, so I want a low Z impurity. I don't want high Z in this, because if I have high Z in this, the machine will radiate like hell. The compromise, unfortunately, tungsten is high Z, but it was used down here because it has extremely high good heat flux resilience, and it's melt loss resilient due to ELMs and disruptions. If I look at materials challenges beyond ITER, going ahead, well, this is the neutron fluence. So for jet, it's basically 0. For ITER, it's 1 dPa, so this is displacements per atom of the first wall. But going to demo, it's enormous. It's 100 displacements per atom. So that's a very large amount of damage that the first wall has to be able to withstand for a power reactor. There are some unexpected challenges with ITER, one of which is that nearly 90% of the ITER components are supplied by in-kind. So here, this is an illustration of where quality compliance is essential, otherwise the machine won't actually fit together. So if people put holes in the wrong place, the machine's not actually going to bolt together properly. There are other unexpected challenges. Design finalization and cost, I already talked about that. But because ITER is also in some sense an experiment in how to manage a research program with many different cultural and country players. So they have different management cultures and different expectations. So the first plasma deadline was originally 2015. It's now shifted out by 10 years to 2025. Here's a picture of it that I took, well, I didn't take, but I ripped off the website from April. You can see the tokamak pit being built. There's the assembly building, cryostats, ITER headquarters, and 400 kV substation. So it is being built. And here's a close-up of the assembly pool and HIT. And indeed, they've already had first plasmas of the electrical fashion. Curiously, there was an operator inside this crane at the time, and he was in a Faraday cage, so he was fine, but he got a shock. So here's some fusion-relevant Australian activity. I don't know how much time I've got, only a couple of minutes maybe. I lead a theory and modelling program at the ANU. The ANU also has a substantial experimental activity spanning both a stellarator and a linear machine. ANSTO has an emerging nuclear science materials program, which is relevant for fusion. There's a number of players that have had an activity in plasma physics and also atomic collision physics, and there's an activity at the University of Wollongong that looks at high temperature neutron resilient superconducting magnets, which is magnesium diboride. A number of years ago, I initiated this activity to try and engage Australia in fusion. We've put together a strategic plan to try and advance and realise that ambition. So we had a number of proposals that we put to the government of the day. Some of these are now coming to fruition. So for example, we proposed funding for an Australian flagship contribution to ITER. My colleague, Professor John Howard, has been awarded an ITER conceptual design contract for an imaging diagnostic on ITER. That's exciting. And also, what excites me is that the research framework of ITER is this international tokamak physics activity, and ANSTO has taken the lead as a legal representation, a legal organisation in Australia, to open a discussion and dialogue with ITER to create some agreement for Australians to participate in ITER. So that's also exciting. And we requested some other things as well. Whether they turn into reality is a function of political will. I mentioned the ITPA. All I really wanted to say was that there's lots of different physics groupings, and this is really where all the plasma physics and much of the technology resides. What's next? Well, finalise this MOU, this diagnostic contract with the facility. I haven't mentioned the wider array of other experiments. There's this €1 billion Wendelstein 7X stellarator that's been was opened by Chancellor Merkel early this year, I think. Together with significant investment in the Asian region. Here's a $3 billion superconducting experiment being constructed in Korea. And there's also, later on this year, Professor John Jekino, who's a senior advisor to the ITER DG, will be here. So I've given you some background. What I want to do is really quickly show, let's suppose I managed to get fusion to work. This is what it would look like. A fusion power plant, at least in schematic form. So it doesn't really look that different to a coal fire or a nuclear fission power plant, except we replace the heat source with a DT plasma. It has a slightly different heat exchange mechanism. That's not that different to fission either. So I'm a bit of I'm motivated by altruism in some sense. So I've already said what fusion on Earth could provide. But I would ask the question, what could ubiquitous near limitless clean power do? Well, maybe it could help lift the developing world out of poverty. It could end wars. It might be able to power large-scale clean water through desalination. That's of interest to Australia. Maybe it could remove some of the screw-up that we've done to the planet by pulling CO2 out of the atmosphere. That would be a good thing to do. And I'm also a bit of a Trekkie at heart, so it might enable extrasolar space travel. So I'll leave it there.
Thanks, Matthew. Let's squeeze one question in. I'm tempted to ask one. The flippant way you talk about neutrons when
Not flippant, but I was trying to compress the talk.
No. I would like some of those neutrons. But someone else? Does anyone else have a question? Good question. We can all talk afterwards.
There, all right, no worries. Okay.
Thanks very much. So yeah, Patrick, you're going to.
How do I do this?
Something that is reasonably makes the accident on fuel world, so I look forward to.
Are you the speaker? Oh, this is the speaker. Sorry. There you go.
Oh, thank you. Oh. Hopefully this will come up in a second. Well, thank you, Julian. That doesn't work. Thank you for the introduction. So yes, I'm going to be talking about fission, accident-tolerant fuels. This is not a technical talk very much. It's more of an overview talk. I must admit, first of all, I'm a materials modeler. I do modeling, but much of what I'm going to talk to you today is actually experiments that we've done. And actually, one thing I should say is that half of my work is about this kind of stuff. The other half of my work is actually around beryllium lights for fusion applications. So that works pretty well with what Matthew was saying. So I'm going to assume that you know mostly how current fuel look like and how they work. So I'm going to very briefly talk about them. And actually I'm going to spend most of the talk highlighting the need to change the current fuel. Why do we need accident-tolerant fuels? And I'll give you an overview of the major candidates for nuclear fuel, accident-tolerant fuel cladding, accident-tolerant fuel. And as I do that, I'll give you two examples of some of the work we're doing at UNSW on accident-tolerant fuel space. That's uranium suicide, uranium nitride composite, and also developing a new max phase for coating of zirconium alloys for oxidation resistance. So yeah, I said I won't spend too long here, but current conventional fuel for light water reactors, or well, for water-cooled reactors, is uranium dioxide, or sometimes MOX as well, but tiny fuel pellets that are stacked into zirconium cladding. The zirconium fuel pins are about 4 meters long and about the width of your little finger. And then you put a lot of those fuel pins together, 17 by 17 array to form an assembly, and many of those assembly form your nuclear core. And then you simply have coolant going through all those fuel pins to extract the heat that's produced inside the fuel pellet, and then drive a steam generator, and get electricity a conventional way. There are good reasons for using these materials. We use CO2, and we've been using it for a long time because it's got really high melting temperature. We use zirconium cladding because it's got good mechanical and chemical properties, but importantly, it's very neutron transparent. And I'll keep on coming back to this point. From the point of view of the utilities, neutrons are very important. You could say that inside a nuclear reactor, neutrons equals dollars. The more neutrons you got, the more money the utilities are making. So you really want to make sure you're not absorbing too many of those neutrons. So why do we have to change if we use those materials and they work? Well, let's consider what happens. What is the response of this material in an accident scenario? This could be a loss of coolant accident, as we've heard before, a reactivity-initiated accident, or, as in this case, a station blackout scenario, which is probably the more severe of the three types. In this graph, you can see what actually happens. Unfortunately, the units here are tens of thousands of seconds, which are not very convenient. So I've put in hours, the equivalent in hours in green. If you have a blackout, you lose your electricity. It means that you lose electricity. All the power, the diesel power generation has failed to come. The backup has failed to come online, and you have no active safety system essentially. So what happens is immediately your reactor shuts down, and that's actually from gravity usually. And then you got lots of coolant just sluggishly not being pumped around, and that gets warmer and warmer. Eventually, at about 2.5 hours, the hottest part of your core will start to dry out. it won't actually be in contact, the fuel pins won't be in contact with water anymore. And as that happens, they start to warm up quite rapidly. That should follow a nice parabolic line, because since your reactor is shut down, the amount of power generation actually should decrease with time from decay heat. And also the temperature difference between the cladding and the fuel should slowly get to an equilibrium. However, if you look at what actually happens to zirconium, which is this black line, you see that it's super parabolic. It goes a bit faster, heats up faster than parabolic. And the reason for that is that if you get a metal and you heat it up, you're increasing the oxidation rate of that metal. And that's true for any metal. Unfortunately, oxidation of a metal is actually an exothermic reaction. So you're producing heat. And that heat contributes to the increase in temperature, which then increases the rate of oxidation, which then produces more heat, and so on. And so you get to this runaway reaction, which happens at about 3.5 hours in a conventional PWR reactor, and that melts your fuel, which is indicated with that solid black line. So if you instead move on to, say, stainless steel, which is this purple dotted line, you can see that the reaction kinetics are a lot slower for oxidation, and you produce less energy in the oxidation reaction. So you actually gain quite some time before the runaway reaction. But the melting temperature of stainless steel is actually much lower. So you actually only get about half an hour. Half an hour is not little. You actually can do a lot in half an hour if you go a station blackout. But we would like to do even better than that, especially if you go through the effort of changing the whole fuel inside a reactor and all the regulations that go with it. So if we look at silicon carbide, you can see that it's got that lovely parabolic curve because it doesn't have an exothermic oxidation reaction, and the melting point is up there, so at 3000 Kelvin. So it sounds amazing as a material. And from the oxidation point of view, it is. However, of course, you have to make this stuff, you have to pay for it, and it has to be mechanically strong. So there are the downsides. This picture here, which I lifted from the review from Zenko, just shows basically the same things in a pictorial representation. And you can see that as the temperature increases, the cladding oxidizes. As it oxidizes, it gets thinner. The amount of metal available gets thinner and gets softer because it's hotter. So it can balloon and burst due to the pressure from the pellet, and then it can melt. The point of accident-tolerant fuels is to try and push this part and this part as far later as possible, so like to the right of this graph, and try and buy time in an accident scenario. But importantly, we must do this without compromising on the economics of power generation. Unfortunately, a lot of alternative claddings, like stainless steel, absorb more neutrons than zirconium, or cost a lot more to make, like silicon carbide. So that can be somehow countered by just simply using higher density fuel. And I'll explain that later in greater detail. However, there's one more option here that I haven't mentioned. Apart from zirconium, stainless steel, and silicon carbide, and a few others, you can actually, there's an approach of keep on using zirconium, which is a very mature technology. We know how it works. But simply coating the outside of it with something that is oxidation resistant. This is a picture from Wisconsin University where they, in fact, have coated it with titanium aluminum carbide, which is a max phase. I'll explain in a second what these are. And the aim of this coating is to have something that is oxidation resistant, but at the same time it has many other criteria that it has to satisfy. It has to be thermally conductive, otherwise you create a thermal barrier from the extraction of heat. It has to be relatively radiation tolerant, scratch resistant, possibly self-regenerating in case you scratch it. And on top of that, it has to be neutron transparent. So we're really asking a lot of this coating. And there's a particular class of materials that seems to nearly satisfy most of them, which is max phases. Max phases are essentially ceramics. They are formed of three elements, M, A, and X. M is a transition metal. A is something that from the semi-metal series. And X is the carbon or nitrogen. Because of the constraints on neutronics, and because we want oxidation resistance, we're limited with A being aluminium, because when you oxidize something that contains aluminium, it forms a nice alumina layer, which is protective. X being carbon, because if you use nitrogen, then you've got problem of activation, though you could get around those. And then you've got a little bit of play with M. And in particular, titanium aluminum carbide and chromium aluminum carbide have been identified as very good candidate materials. In particular, titanium aluminum carbide sticks very well with to zirconium cladding. chromium aluminium carbide has excellent corrosion resistance. The corrosion resistance of this is also quite good. Our idea was, can we make something, can we tailor the properties both of the lattice parameter to get it to stick to zirconium and the corrosion resistance by making a mixture? So we tried to make a mixture, and unfortunately, the very end, so adding very little chromium to titanium aluminum carbide, or very little titanium to chromium aluminum carbide, actually gives you lovely single-phase max phases. And this is the typical diagram of the cleaved surface, and you can see this laminar structure, and they're actually rather beautiful structures. But as soon as we tried to mix more than that, we didn't get what we wanted. We didn't get a single max phase. We got a whole bunch of other things. Got titanium carbides, aluminum chromates, and fortunately, even though we weren't trying to make it, we got a chromium titanium max phase, but notice the stoichiometry. This is a different type of max phase. It's 3-1-2 rather than a 2-1-1 max phase. So it's a high order max phase. But then we figured, well, we weren't trying to make it, but it formed even without us trying to make it, so perhaps that was the way forward. So we tried to make some of these titanium chromium 3-1-2 max phases. And we could make the titanium one. The chromium one is known not to exist, so that's fine. We didn't care about that. And we could make this 60% chromium, but anything in between, again, we failed. They just don't want to form. You just can't get solid solutions. Nevertheless, we looked at the corrosion properties of this. We tried to oxidize them. And what's interesting is that, so the parent metal, we know that the parent max phases, we know they're very good corrosion resistance. Interestingly, this stuff that, I must say that one has terrible oxidation resistance. The new phase that we formed, the 2/3, 1/3 chromium, titanium, aluminum carbide, it just disintegrated in air. It's absolutely dreadful. Though it's very interesting I've got a couple of publications on why this forms, which is very interesting from a materials point of view. From a practical point of view, the most oxidation tolerant were actually these ones. That actually, and it wasn't because of the max phase, because we know that max phase is not very oxidation resistant. It's actually because of all the other crap that we were trying to avoid. So you get things like, this is the example. This is the most oxidation resistant sample we have, which has got a nice alumina layer. And it's because of this aluminum chromate and the chromium carbide that you form there. So it kind of brought our attention to perhaps max phases are on the way forward. Perhaps there's nothing wrong with using an aluminum chromate or chromium carbide mix. So that's where we're going next. But we've learned a lot on the way. We've learned a lot of physics about this quaternary max phase that we're now applying to other max phases. So I spent a lot of time talking about claddings. But there's more to the cladding. There's also the fuel. As I mentioned before, and I've only got a couple more slides, you can, to offset some of the cost of the neutronics of accident-tolerant cladding, you can use higher density uranium fuel. Because if you have a material that actually contains more uranium atoms, you actually need to reach it to a lesser extent to achieve the same reactivity. And that means saving money on the enrichment. Or the other way of seeing it is you can keep on enriching for the same to the same level by using a high uranium density. Means you can then use a cladding like stainless steel or something that absorbs more neutrons without losing reactivity, therefore without losing money. I apologize, that graph didn't come out very well, but it's about the second point, the thermal conductivity. If you go through the effort of actually changing your fuel, you might try and do more than just increasing the uranium density. You might try, for instance, increasing the thermal conductivity, because that's what decides what is the maximum temperature inside your fuel. So the outside temperature of your fuel pellet, which is supposed to be in this graph, is completely governed by the coolant. If your coolant works at 350 degrees C, that's the outside temperature of your cladding. The inside temperature of the fuel is simply dictated by how fast can you move the fuel out from the inside of the fuel to the outside. So the thermal conductivity. And higher thermal conductivity means lower internal maximum fuel temperature, which is good because you're further away from your melting temperature. But it's also good because it means you've got less energy stored at the beginning of an accident scenario. The last point is the heat capacity. This is often not mentioned, but it's actually quite important. If you've got materials with a high heat capacity, you need more heat to increase the temperature. So in an accident scenario, you get a slower thermal response to an increase in heat production. So just comparing some basic properties of some uranium compounds, and this is only you look at uranium. Of course, one could look at thorium, plutonium, and other potential fissile material. comparing them with uranium oxide, you can see that, first of all, the melting point of uranium oxide is incredibly high, and we're probably not going to beat that. But the thermal conductivity of uranium oxide is absolutely dreadful. There are two good aspects about that. First is that when you irradiate the material, the material's degradation, the fact that the thermal conductivity degrades, doesn't matter, because it's so crap to start that it can't get any worse. So that's one good aspect of it. The other good aspect is whatever material you come up with is going to be better. And that means that actually melting point matters less. Because if you get such a good thermal conductivity as some of these materials have, then the melting point can be much lower. And particularly, you should notice uranium nitride, which has a very high melting temperature, incredible thermal conductivity, and I'm cheating slightly because I'm only showing you the room temperature one. It does get worse as you increase the temperature of the material. But it's still very good. And the uranium density is actually very, very high. So it looks like an amazing material, and it is on paper. It's got the very bad downside that is very poor. It has very poor oxidation resistance. So this is an experiment. This is courtesy of Westinghouse, an experiment performed at Los Alamos where they oxidized uranium oxide, uranium silicide, and uranium nitride just disintegrated. And that's in water at 300 degrees C, so not very hot. So the question is, can we create a compound that has all these lovely properties of uranium nitride but doesn't oxidize like buggery? Ooh, and this is my last slide. I'm conscious of time. Well, we're working with KTH in Sweden and Westinghouse to develop these materials. We're not the first to have come up with this idea, but we believe that KTH are the ones who have done it the best, which is to create uranium nitride surrounded by uranium silicide inside each grain. And that's by spark plasma sintering. This is a work showing that this has been done before, but the microstructure wasn't quite as good because you get some ternary phases forming. Now, if the material properties are so good because of the microstructure, then the obvious question is, yeah, we can make this lovely microstructure, but when you put it in an accident scenario, do you retain this lovely microstructure, or do you change the microstructure and therefore get something that oxidizes very badly? And so that's what we're doing right now. And this is a project led by Edward O'Bard on the floor, actually. We're working with KTH, ANSTO, and Westinghouse to do in situ heating of this composite material while we do neutron neutron diffraction to see if at high temperatures you do start forming ternary phases or not. And that's just looking at the thermal effect. And then what we want to do in the future, and this is probably 2017, is actually irradiate the material. First with ion irradiation, and then we'd like to go to neutron. And with that, I finish. Thank you.
Thank you, Patrick. You've earned yourself a question.
Thanks.
I always say it's very hard to start on nuclear fuel because it's very hard to stop.
Well, not so much a question, just a compliment. I thought that was an excellent presentation. I have a relatively rudimentary understanding of the basic nuclear fuel, starting with fuel oxide. That was extraordinarily interesting. I didn't know there was so much potential to improve, so that was great.
Thank you.
Very interesting work.
Thank you.
Okay, and we're very lucky to have Rita Falsterton from Westinghouse to join us.